What lies beyond the edge of everything we know? For thousands of years, we looked up at the stars and wondered about the darkness between them. But hidden in that darkness are objects so extreme they defy everything we thought we knew about reality. Black holes are born in the violent death of massive stars when gravity becomes so powerful that nothing can stop the collapse. The core collapses so completely that it tears a hole in the fabric of spacetime itself. In 2019, we captured our first image of a black hole. This is M87 star, 55 million light-years away, with a mass 6.5 billion times our Sun. At the heart of our own Milky Way lurks Sagittarius A star, a supermassive black hole containing 4 million suns. Join us on a theoretical journey to answer humanity's most mind-bending question: what's inside a black hole? Our destination is a supermassive black hole, 10 billion times the mass of our Sun. From a safe distance, it's beautiful, a glowing disk of superheated matter spiraling into oblivion. The accretion disk burns at millions of degrees, matter compressed and accelerated to nearly the speed of light. Black holes feed on everything nearby: stars, planets, gas, dust, even light itself. Some black holes shoot jets of particles across thousands of light years, powered by the raw energy of infalling matter. As we approach, space itself warps. The black hole's gravity bends light from stars behind it, creating distorted mirror images. This is gravitational lensing. The black hole is so massive, it acts like a cosmic magnifying glass, warping all light around it. We pass through a graveyard of worlds, the shattered remains of planets and asteroids that ventured too close. Even stars cannot escape. This companion star is being slowly devoured, its outer layers torn away by tidal forces. At 1.5 times the event horizon's radius lies the photon sphere, where gravity is so strong that light itself can orbit the black hole. This is the innermost stable circular orbit, the last place matter can circle before it falls. Beyond here, there is no turning back. Ahead lies the event horizon, the boundary of the black hole itself. Once we cross it, not even light can escape. The event horizon, the point of no return. Its size depends only on mass. For our black hole, it's 60 billion kilometers across. As we approach, time itself dilates. To outside observers, we appear to freeze, taking forever to cross. But for us, time flows normally. And then we cross. Surprisingly, there's no barrier, no wall. The event horizon is simply a mathematical boundary in spacetime. But the laws of physics have fundamentally changed. Space itself now flows inward faster than light, making escape impossible. We are now inside a black hole. The outside universe appears as a shrinking disk of light behind us, redshifting toward darkness. Inside the event horizon, space and time swap roles. Time now points inward toward the singularity. Moving forward in time means moving inward in space. Just as you cannot avoid moving forward in time outside a black hole, you cannot avoid moving inward toward the singularity inside one. Gravity here is not uniform. The pull on our feet would be stronger than on our head, beginning a process called spaghettification. For a stellar mass black hole, these tidal forces would tear you apart atom by atom before crossing the horizon. But in a supermassive black hole like ours, the event horizon is so large that tidal forces are survivable, at least at first. But as we fall deeper, the environment becomes increasingly alien. Light behaves in impossible ways, and space itself seems to fold. Some theories suggest a firewall of intense radiation exists at the horizon, protecting information from destruction. This is the black hole information paradox. Quantum mechanics says information cannot be destroyed, but black holes seem to erase it completely. Stephen Hawking showed that black holes aren't completely black. They emit faint radiation by stealing energy from virtual particles at the horizon. As we near the center, the tidal forces become overwhelming. Everything is stretched, compressed, and torn apart. At the center lies the Singularity, a point of infinite density and zero volume where all the black hole's mass is concentrated. Here, our physics breaks down completely. Gravity becomes infinite, and our equations return only nonsense. General relativity predicts the singularity, but quantum mechanics suggests something else must happen at these extreme scales. To truly understand what is at the center, we'd need a theory of quantum gravity, unifying Einstein's relativity with quantum mechanics. String theory suggests the singularity might be replaced by a fuzzy ball of Planck-scale strings, avoiding the infinite density problem. Loop quantum gravity offers another possibility. Space-time itself is made of discrete loops, and the singularity becomes a bounce point. If the classical singularity exists, space-time curvature becomes infinite, and all directions point inward to the same infinitesimal point.
Some solutions to Einstein's equations suggest black holes might contain wormholes, tunnels to distant parts of the universe, or even other universes. Theoretically, these wormholes could connect to white holes, the time-reversed versions of black holes that expel everything. Some theories suggest every black hole might contain an entire universe, making our cosmos just one bubble in an infinite multiverse. The truth is, we don't know. The singularity remains one of physics's greatest mysteries, hidden forever behind the event horizon. Every star, planet, and particle that ever fell in is here, compressed to infinite density, their information perhaps preserved in ways we cannot yet understand. Black holes are not eternal. Through Hawking radiation, they slowly evaporate, though it takes longer than the current age of the universe. For every particle that escapes as Hawking radiation, the black hole loses a tiny amount of mass and energy. Paradoxically, smaller black holes are hotter. A black hole the mass of our Sun would have a temperature just billionths of a degree above absolute zero. A black hole with our Sun's mass would take 10 to the 67 years to evaporate completely, trillions of times longer than the universe has existed. In its final moments, a black hole would release its remaining mass in a brilliant burst of energy, visible across the cosmos. Tiny black holes might have formed in the Big Bang's earliest moments. Those smaller than a mountain would have already evaporated by now. Some theories suggest the information isn't destroyed. It might be encoded in the Hawking radiation itself, preserved through quantum entanglement. The holographic principle suggests everything inside the black hole is encoded on its surface, like a hologram containing 3D information in 2D. If information is preserved in the radiation, it might theoretically be possible to reconstruct everything the black hole ever consumed. But the information paradox remains unsolved. We still don't know if information is truly lost or preserved in ways we don't understand. In reality, escape is impossible, but for our journey, we return from the edge of physics itself. Crossing back through the event horizon, the universe expands before us again, and time resumes its familiar flow. As we retreat to safety, the black hole becomes beautiful again, its dangers hidden behind the event horizon. Black holes aren't just destructive. They help build galaxies, regulate star formation, and shape the cosmic web itself. There are likely 40 quintillion stellar black holes in the observable universe, and nearly every large galaxy harbors a supermassive one at its heart. In 2015, we detected gravitational waves for the first time, ripples in spacetime from colliding black holes billions of light-years away. When black holes collide, they release more energy and gravitational waves than all the stars in the universe emit as light in that moment. The Event Horizon Telescope linked radio telescopes across Earth, creating a planet-sized telescope to photograph a black hole's shadow. New observatories will reveal black holes in unprecedented detail, testing the limits of general relativity and quantum mechanics. Black holes are nature's laboratories, pushing physics to its absolute limits and revealing where our theories break down. Understanding what truly happens at the Singularity requires quantum gravity, the holy grail of theoretical physics. Black holes have revolutionized our understanding of spacetime, thermodynamics, information theory, and the quantum nature of reality itself. At the heart of our galaxy lies Sagittarius A star. We orbit this supermassive black hole from a safe distance of 26,000 light-years. We return to Earth changed. Having glimpsed the edge of reality, we see our world with new wonder and appreciation. The universe holds infinite mysteries. Keep exploring. Subscribe for more cosmic journeys.